Okay, we're going to do one more of these lectures online. This one is to introduce you to cylindrical polar coordinate system. So for most of your work in intro physics courses, you worked in Cartesian coordinate systems. That is just sort of the x hat, y hat, z hat coordinate system. And today I'm going to introduce a different coordinate system that can be useful in certain situations, certain problems that involve rotation. And okay, so let's go ahead and get started. So in particular, what we're going to do today is figure out how to write down position, velocity, and acceleration vectors in cylindrical polar coordinates. Cylindrical polar coordinates. Sometimes people just say polar coordinates here, but I'm using cylindrical polar because there's another coordinate system called spherical polar coordinates, which is different. So this is the main topic today. So, all right, so let's just start off with a diagram to illustrate what this cylindrical polar coordinate system is about. So, in fact, we're going to start with drawing this diagram on top of a sort of typical Cartesian coordinate system. So if this is the x hat direction over here, this is y hat, and this is z hat, then now what we're going to do is, in order to demonstrate to you what the meaning of the cylindrical polar coordinates are, I'm going to first draw a structure on top of this Cartesian coordinate system. The structure is a quarter of a cylinder. Okay, so imagine a cylinder which is centered around the z-axis. So, and I'm just going to draw a quarter of this cylinder, the quarter of it which is contained in this positive x, positive y part of the volume. So that would be the part of the cylinder that intersects the xy plane. And let's see, so now let's draw one edge of that structure. Okay, so that is supposed to look like 1/4 of a cylinder. If you were to draw the complete cylinder, it would go all the way around. Describing the position, velocity, and acceleration of a particle, which is located right here on this upper edge of this quarter cylinder. Okay, so let's just, as a starting point to make reference to what you already know, let's write that down in the Cartesian coordinate system first. Okay, so the position, which we'll represent by r vector, is, as you know, it's just the x component times x hat plus the y component times y hat plus z component times z hat. So remember, the x hat, y hat, and z hat are just unit vectors pointing in those x, y, and z directions. Okay, so maybe we can illustrate those Cartesian coordinates in green here. So if you imagine a vertical line coming down, and then this length here is the y coordinate, this is the x coordinate, and let's see here. So the z coordinate then is this height from here all the way to here, or this height here from here to there. Okay, now we're going to, if we're interested in writing down the velocity, then in Cartesian system, this is just taking one time derivative of the position vector. So time derivatives in this course I'll often denote with a dot. So one single dot is one single time derivative of r, and as you know, that's just x dot x hat, y dot y hat, plus z dot z hat. Now, the reason that step was simple was because the unit vectors x hat, y hat, and z hat don't depend on time. No matter where this particle goes, the x hat, y hat, and z hat vectors never change their direction or their magnitude. So these unit vectors do not have any time derivative. Their time derivative is 0. Therefore, it's easy to write down velocity. Similarly, if we want to write down acceleration, it's just one time derivative of the velocity. And again, since the unit vectors don't have any time dependence, it's easy to write this down. 2 dots indicates 2 time derivatives, the second time derivative. Okay, now the situation is not so simple in cylindrical polar coordinates. So in that case, as you might have gathered by my foreshadowing, the unit vectors in cylindrical polar coordinates do depend on time in general. So let's let's now draw on this diagram how to represent this location of this particle in cylindrical polar coordinates. And then we'll figure out what are their time derivatives to get their velocity and acceleration. Okay, let me just do that now in green again. Okay, so and to represent the position now in cylindrical polar coordinates, again we'll have 3 coordinates, and this time one of those coordinates is called rho, and rho is this distance from the z-axis to the point, and the rho, that line that I just drew, makes a 90-degree angle with the z-axis. So it's a line that goes straight out from the z-axis to the point, and the length of that line is the coordinate rho. Let me draw that projection of that line on the xy plane here. So again, if this, so this line here is length rho. That's the Greek letter rho. Now the second coordinate of cylindrical polar coordinates is this angle, which is usually given the Greek letter phi. So phi is the angle between the x-axis in Cartesian coordinates and this line here, which is the projection of that rho line. Okay, now the final coordinate in cylindrical polar coordinates is z, and z is just the same as it is in Cartesian coordinates. It's just the distance from this xy plane up to where the point is located. Okay, so now, what are the direction of the unit vectors? So there's one unit vector for each of these 3 coordinates. So the 3 cylindrical polar coordinates are rho, phi, and z. If you specify rho, phi, and z, then you have the position of the particle. So what are the unit vectors? One unit vector is the one that points, it's a continuation of this line, so it's in this direction, away from the z-axis, towards the point that we're talking about. The phi unit vector is pointing tangent to this circle, so it's pointing directly that way. It's perpendicular to that line, that vector that I've drawn from the z-axis to the point, and it's tangent to this outer edge of this cylindrical piece that I've drawn. And then finally the z-hat direction is still just straight up as usual. Okay, so why is this, as I mentioned before, the unit vectors in cylindrical polar coordinates can depend on time, and why is that? So if you imagine this particle just moving around in a 3-dimensional volume, then as it moves around, the direction, not the magnitude, but the direction of both rho hat and phi hat will change. The direction of z hat is always just straight up, so that doesn't change. But the direction of rho hat and phi hat changes in general as you move a particle around and you're describing it with these cylindrical polar coordinates. Okay, so let's go ahead to move forward. We're going to first write down this vector in a sort of mix of polar and cylindrical, polar and Cartesian coordinates. So we're going to rewrite the r vector. I never wrote this down actually. So the r vector is the vector that goes from the origin here to our point right there. That's the r vector, not to be confused with rho. R is the vector that is just from the origin to the point. Okay, so now as you can see, you can relate the x-coordinate in Cartesian coordinates to rho and phi. So x is equal to, so the x-coordinate of the location of this particle in Cartesian coordinates is equal to rho cosine phi, right? You have to imagine again this rectangle in the xy plane. So cosine phi is equal to x over rho. Okay, and that's in the x hat direction. So I'm just rewriting the magnitude of the x component in terms of rho and phi. Now let's do the same thing for the y component. That's just rho sine phi in the y hat direction. Now in order to get this vector totally in terms of polar, or the cylindrical polar coordinates, then we need to rewrite x hat and y hat in terms of, we need to rewrite all of this in terms of, in a way that includes the unit vectors rho hat and phi hat and z hat. Okay, so I guess we should add in there that we have z hat. That's not changing. Okay, so in order to rewrite this, so the next step here is going to depend on figuring out the relationship between x hat, y hat, and rho hat and phi hat. So first, let's just make an aside here. This is an aside about unit vectors. And in general, if you want to know how to write down a unit vector, this is the general definition. So if you want to know the unit vector associated with, say, the x hat direction, the way it's defined is you figure out what's the change in, so if you take your particle and you move it a little bit in the x direction, how does its position vector change? And that's what we do here. So if you take that change in the position vector divided by the magnitude of the change, that is, by definition, that's x hat. Okay? And in general, you can do this. So if you want to know what is the unit vector in the rho hat direction, then you take that change, divide it by its magnitude. Right? It's always a magnitude 1 thing, right? If you divide the vector by its own magnitude, it's always going to have unit length. Okay, so we're going to go ahead and do that. We're going to take this r vector, take its derivative with respect to rho. So then, all right, so dr d rho, using this expression for r, is equal to cosine phi in the x hat direction plus sine phi in the y hat direction. And now if we take the magnitude of that thing and divide it to rho, then that's taking this thing and dividing it by the magnitude of that numerator, which is just going to be cosine squared phi plus sine squared phi. That's the magnitude of the vector in the numerator here. And as you probably know, the trig identity for cos squared of an angle plus sine squared of that same angle is 1. So this guy already has the magnitude of this vector is already 1. So the answer for what is rho hat, it is cosine phi x hat plus sine phi y hat, which lo and behold is sitting right here, right? So if we want to write down the position vector in cylindrical polar coordinates, it is rho times rho hat. That's this guy, right? That's rho times that thing plus z times z hat. That's still keeping the z coordinate there. That's it. That's the whole thing. You might be thinking initially, where's phi and where's phi hat? But position vectors in this coordinate system do not have a phi component. And it makes sense if you think about it. Phi is always exactly perpendicular to this r vector. So the position vector never has a phi component. That's one fundamental fact about the cylindrical polar coordinate system. Okay, so to move forward now, what we need to do is take a derivative of this to get to the velocity. So, all right. So let's take one derivative to get velocity in polar coordinates. So if we take the time derivative of this, we get rho dot rho hat. Now, but rho hat itself depends on time if the particle is moving around. So you also have this term. I just used the product rule on this first part of the sum here. Plus z dot z hat. And now z hat is still, it's always stationary no matter where the particle goes, so there is no second term in the product rule for that term. Okay, so we have to figure out what is rho dot hat. Rho hat dot, I mean. All right. So let's go ahead and do that. So we found out before that rho hat is, I just erased it actually, so maybe we could write this down here. So rho hat was this cosine phi x hat plus sine phi y hat. Therefore, so where rho hat dot is equal to one time derivative of that. So one time derivative of that thing is minus sine phi dot x hat, and there's no time derivative of x hat, plus cosine phi of phi dot of times y hat. Okay. And just to be clear, these are multiplied. So cosine phi times phi hat. Sine phi times phi hat. Or phi dot, sorry. Okay. Now, we're going to do one more step with unit vectors. Let's figure out what is the phi hat unit vector. So the phi hat unit vector, we have to figure out what that is. So again, we just do the same strategy. What is the change in r with respect to the change in phi? And we take that thing and divide it by its own magnitude. Okay, so remember, we'll take this version of r, take its derivative with respect to phi. So let's get the numerator. The numerator there is going to be equal to rho minus rho sine phi. That's the derivative of this with respect to phi. And that's in the x hat direction, plus we've got a rho cos phi in the y hat direction. This term has no phi dependence. Now we've got to take all of that, we've got to take that term and again divide it by the magnitude of itself. So its magnitude is rho squared sine squared phi plus rho squared cosine squared phi, which if you factor out a rho squared, this thing, so this is, remember, this is phi hat by definition. So our phi hat is equal to, let's see if I can squeeze this in a little better. Divided by, remember, we'll factor out a rho squared, and then sine squared plus cos squared is 1. So we just have a rho in the denominator here. So square root of rho squared. So the rho's all cancel. And what we're starting to see here is that phi hat is in fact buried in here. Okay? So rho hat dot is equal to, let's see if we can factor out one of the phi dots. Phi dot comes out, and then you have a minus sine phi x hat, plus a cos phi y hat. So this is phi dot phi hat is equal to rho dot hat. All right, so there we have now an expression for the velocity in these cylindrical polar coordinates. That's this term plus rho phi dot phi hat. That's this term plus z dot z hat. That's that last term. So there is the velocity. All right, we're getting there now. We've got to do the acceleration now. And then we'll be done with this. Once you have these expressions, they can be very useful. So you can start doing things like, once I have an expression for the acceleration, I can just, if I can express a force also in the same coordinate system, you can write down Newton's laws in this coordinate system and solve certain problems more easily. Okay, so let's free up some space here for finding a hat, this acceleration. Okay, so we got to take the time derivative of this. That is equal to, let's take care of this first term first. Just using the product rule on the first term. Now, this guy's got 3 terms. So the first time I'm just going to take the derivative of the first guy. Now the second part of the product rule will be rho times the derivative of those two things together. So the derivative of those two things together is another application of product rule. That's that stuff is this term. And then our old friend z, so easy to work with. All right, so let's see if we can simplify some of this. Well, we know already that rho hat dot, we know what that is. We just figured that out a few minutes ago. So this term, if we rewrite rho hat dot, becomes, so the rho dot, and then we have phi dot phi hat. Phi dot phi hat is rho hat dot. Okay. Now, what is the time derivative of let's see, this guy? This guy we can rewrite as phi dot squared rho hat. All right, So now we're ready to rewrite these terms, grouping together terms with the same unit vector. So we've got rho phi dot squared, rho hat. So this is not going to be a nice, simple, small expression, but nonetheless, even though it looks rather beastly, it can be quite useful in certain problems. So let's see, we got 2 rho dot phi dot. That's 2 phi dot. And those are all the phi hat terms, and then we got the z term. Okay, so that is the expression for acceleration in cylindrical polar coordinates, and we're done.